Today we shall discuss the photovoltaic cell. The photovoltaic cell is a very important source of renewable energy and it is used in several renewable energy applications. It is one of the most popular renewable energy sources and we shall try to understand how it works, what is its IV characteristics and how it is modeled. Let us first draw the symbol of the photovoltaic source. This symbol is something that we will be using at several places in circuit diagrams. It is a rectangular box and to it the top and bottom are attached to terminals, and inside the rectangular box two straight lines are shown like this, which makes it look like a post cover or an envelope. And to the terminals we can draw it out and attach the terminals, and one side being the positive. Now this is the symbol of a photovoltaic cell or a photovoltaic source, and this can represent a cell, it can represent a module, it can represent a panel, it can represent an array. It depends upon where you want to use it in the circuit diagram, but this photovoltaic cell has a symbol in this form as shown. It has two important parameters. The voltage across the cell, which is called Vt, and the current through the terminals, the current coming out of the positive terminal, if it is connected to the load, will be called It, or the terminal current It. And most of the devices are characterized by these two variables: the voltage across the device and the current through the device. And the IV characteristics are an important graph which gives insight into the particular device. So let us draw the IV characteristics. So let me draw the two axes. The x-axis is Vt, the terminal voltage, and the y-axis is It, which is the terminal current. So if you take a normal voltage source, how does it look like? So a voltage source will be a line where you will see that the voltage is constant, and this is typical of all voltage sources, DC voltage source, and this is the symbol for that. If I am having a current source, how would it look like? A current source would have a current which is constant, which is fixed, whatever may be the voltage, and that is having a symbol like this. The photovoltaic source is neither a current source nor a constant voltage source. It is in fact both. It is a mix of both, and it has a characteristic which is like this. So this is this curve, the blue curve is the IV characteristic of a photovoltaic cell or a photovoltaic source. So you see that it behaves as a constant current source for some part of the operating points, and for some part of the operating points it behaves as a constant voltage source. So it's actually a mix of both a constant voltage and a constant current sources, and then you have the merging of the two aspects coming in there. Okay. So how did we get this characteristic? Let us study about the photovoltaic cell a bit more in detail and arrive at the model of the photovoltaic cell. So let us consider this solar PV cell, and let me put down the IV characteristic XY axis only. Okay. So x axis is Vt, the terminal voltage, y-axis is the current IT. Now the PV cell is nothing but a PN junction, just like a diode. So let us start with the diode. Let us replace this and then put in place a diode, which is a PN junction. This is the anode and the cathode. However, for the PN junction diode, the current direction is not in this direction. The current flows into the anode, comes out of the cathode, the conventional current direction. Okay. Let me mark that. So let's say that through the diode, this is the current direction, and this is negative of the current direction that we have indicated for the terminal current IT. So it is minus IT. So minus IT will flow through this diode, PN junction diode. So let us mark it on the IV graph. So the axis will be like this. So it is on the negative part because the current flowing into the anode, cathode, or the PN junction, it will be the negative part here, and let me mark that as the minus IT current. So for this, the minus IT VT curve of a PN junction is well known to us. So let us draw that. So it is something like this, and we have a cut-in or a knee voltage of around 0.6 volts. However, now there is a new addition, and that is light, photons. So light impingance falls on the PN junction cells, the diode, the PN junction diode, or the PN junction cells, and that is going to excite the electrons which are there in the valence band into the conduction band, which means that it is going to give up the photons. The photon energy packets are given to the electrons, and the electrons will raise from the valence to the conduction band and then start flowing in the conductors. So this light as a new item that comes into play is like a current source. So let us draw that. So let me put a current source in place. So this current source is going to represent this light falling on the PN junction, and because of the light falling on the PN junction, the photons give the energy to the electrons and raise it to the conduction band, and thereby you have a photon current flowing in this constant current source, equivalence. So let us say you have photons flowing because of light incident on the panel, PN junction panel. There is going to be current flowing into the diode, so that is the diode current ID, and the remaining part of the photon current is going to flow in this direction along the indicated terminal current direction, and because this is positive, that gets raised. If you see that because there is a positive current going through the terminal, if an external load is connected across the terminal, the characteristics, because ID is going to flow through this one, this is the ID characteristic, this is the ID characteristic. So there is a DC shift, so this whole characteristic will shift up because of the excess photon current flowing through the external terminals. So that is how the characteristics shifts up, and this becomes the terminal characteristic of the PV cell together with the PN junction and the current source, which is actually the current source induced by the light. So now you see the IV curve of the PV cell having some part of the characteristic which resembles a constant current, and there is some part of the characteristic which resembles a constant voltage, and therefore it is a combination of both constant voltage and constant current sources. Here is a photovoltaic cell. This is a single photovoltaic cell. This is a polycrystalline cell, approximately 9 centimeters by 9 centimeters. This is the surface on which the solar insolation falls, solar light falls on this, and this is the backside surface. So actually on the surface on which the solar insolation falls is where the N-type material is there, and then on the back side is the P-type material. This is the metallization that you would see, metallization, the contact that contacts with the P-type, and here is the metallization for contact with the N-type. So what we shall see is that this being a single cell, a single p-n junction, many such cells will be joined together to form a module. So we can try to measure and see this back and the front metallization. Let me give an insulation here, and let me fix a crocodile clip like this, so that it makes contact on the backside metallization. This is positive p-type, and on this side this metallization contacts will represent the negative, that's the N-type. So let me bring in a multimeter. So now let me fix this positive of the battery of the multimeter to this crocodile clip. And the positive is making contact with the backside metallization, and on the front side, okay, I am placing the common of the multimeter. So it is showing some around 0.19 volts or 0.2 volts or something like that. Okay. So probably if I cover the plates, the solar cell with my hand, so some of the light, incident light, is cut off, and you will see a lesser voltage, so 0.09 volts or something. So I have a mobile, and using a mobile light source, I am going to check that there is an increase in the output voltage that you would see, which means that the characteristic has raised still higher because there is more photon current. So when I remove the light, so the photon current is decreased, and you will see a characteristic which has moved down, and therefore you will see an open circuit voltage which is lower. Let us now extend this model. This is a first level model. As I said, this does not contain any non-idealities. Let us extend this model to include some resistive non-idealities, both series and shunt. Consider the IV characteristic as I am writing here. You have Vt and It. So let me draw the constant current portion and a constant voltage portion. Your IV characteristic will be within this rectangle. Without non-idealities, we would have an IV characteristic which is something like this, with a curve here and bounded by that rectangle that we initially drew. However, in practice, you will see that there are few non-idealities that come into play. The model that we have with us till now is this current source, which is representing the solar insolation and resulting in a photocurrent, and we have this diode. So across the terminals you have Vt and It, resulting in a characteristic as given by this blue curve. So now let us say that this part of the line, which is supposed to be a real constant, will have a slight slope like this. This represents a series resistance drop. So as the current increases, you will see that the drop from the constant voltage line keeps increasing. This is the IR drop. So if you say that the series resistance is RS, then this slope here would represent the series resistance in the model. So this corresponds to the series resistance drop, and the slope here would be 1 by RS modulus of that, because this is a negative slope. So let us incorporate this in here. So this would be the series resistance part RS. Likewise, the line here will have a slight slope as shown here in red. It will not be perfectly horizontal as shown in the ideal case. So this would be due to a shunt resistance. If there was a shunt resistance, the current source, part of the current from the photon current from the current source will get diverted into a shunt resistance, and that is the drop that you see here, the current drop, which does not reach the terminal current. So this will have a slope again, and that is 1 by R shunt, because current is in the vertical and the horizontal is the voltage axis. It is 1 by R shunt and 1 by RS. So the shunt resistance will come in shunt, as the name implies. This is R shunt. So this would represent the model of the PV cell along with the series and shunt non-idealities. So if we complete the curve, then we get a more realistic IV characteristic of the PV cell, and this model represents the model of the PV cell. This is a very popular model. There's a resistive model with resistive non-idealities alone, and used extensively in the literature.